Dear fellow physicists, my name is Francesco Sorrenti, a PhD student of the Department of Theoretical Physics in Ginevra, and I'm going to present a communication with title Towards Reconstruction of a Large-Scale Matter-Power Spectrum. Measuring the distribution of matter on large scale is one of the goals of future cosmological surveys as Euclid. It could provide information about many issues, such as the total matter density, dark energy, and anomalies in the cosmic microwave background. Actually, performing these measurements at very large scale is difficult due to many experimental limits. Therefore, in the last years, procedures for reconstructing indirectly the large-scale structure have been proposed. Among these, in a paper published last year, Lee et al. Proposed to do it using information about how the large-scale structure affects the small scales. It is a new and absolutely interesting framework that seems to be really fruitful, as the present work is going to show. As we can see in the figure in the upper left, at large scales, it has small values of momentum k, the nonlinear matter-power spectrum coincides with the linear one, while this is not true at small scales. The former is bigger due to the growing contribution from nonlinearities. These nonlinearities imply correlations between different scales, depending on the large-scale environment, as we can see in equation 1, where, to second-order imperturbation theory, the Fourier transformed to point correlation function on the left-hand side is related to the linear density contrast at large scale delta 1 KL on the right-hand side, in the squeeze limit Ks KL minus Ks much greater than KL. Therefore, studying this correlation, we can get indirect information in order to reconstruct the large-scale matter-power spectrum. Using the knowledge from relation 1, we can formulate a quadratic estimator for large-scale modes, summing over as many pairs as possible with a weight function g, equation 2, where the normalization factor A is obtained requiring that the ensemble average over the estimator is equal to the true value of delta, equation 3a. Using this estimator, we get the relation 3b, where in the right-hand side, beyond the term of nonlinear matter-power spectrum, we have a noise term n, due to the fact that the large-scale structure is observed not directly. It is possible to minimize this noise using an appropriate weight function g for the quadratic estimator. We get that the minimized noise is equal to the normalization factor A, as we can see in the expression for the error associated to the reconstructed matter-power spectrum, equation 4. So far, we have neglected the redshift dependence, focusing just on a snapshot. In fact, we do not have access to the full matter field for every values of momentum inside the light cone, but just for the thin shell from which light has reached us. To do so, we need to define the matter-power spectrum over the light cone PLC, whose formulation is slightly more complicated than the one for the matter-power spectrum at fixed redshift. Following Yamamoto et al., we can introduce a useful approximate definition of PLC as the weighted average of the power spectrum over the survey comoving volume V, with weights given by the squared mean comoving number density n of objects at a given redshift. In both the relation 5 and 6, we took into account an extra term, the bias function. Galaxy surveys do not measure the matter power spectrum, but the galaxy power spectrum, which is related to the matter power spectrum through the bias function B. At large scale, the bias can be considered scale independent, while concerning the redshift dependence, in our work we assume the simple linear redshift relation in equation 7, where B0 is the present time value. Once we introduce the formalism of large-scale structure reconstruction, we discuss a possible application, taking as a case study the future spectroscopic survey Euclid, whose launch is planned for 2022. We consider the spectroscopic specification in slide concerning redshift and expected number density observed. We apply our formalism to a synthetic standard dataset of 30 points, obtained using the Boltzmann code COM via Python programming, with the reference parameters in table. In particular, we are considering an extended cosmological model with massive light neutrinos. We are able to obtain an extended dataset with 9 extra points reconstructed at large scale. In this way, we increase by at least an order of magnitude our knowledge, as we can see in the figure in slide, where the red points are the standard dataset ones, and the green points are the reconstructed ones. Once we reconstructed large-scale matter power spectrum, we would like to investigate if and how introducing information about large scales improves our constraining power on cosmological parameters. To do so, we develop a code executing a Monte Carlo Markov chains MCMC analysis on both datasets. We perform a statistical analysis in a Bayesian framework using the Cobaya software. Cobaya is a framework for sampling and statistical modeling, which allows to explore an arbitrary prior or posterior using an MCMC sampler. It supports MPI parallelization too. We exploit this feature to run our code on a HPC cluster provided by Cineca. We also assume Gaussian likelihood and diagonal covariance. The result of the MCMC sampling are then analyzed using the GetD software. In the code, we vary one or more cosmological parameters, as we can see, for example, in this triangle plot, where we assume variable the total mass of neutrinos, the density parameter of cold dark matter omega c, the spectral index ns, and the bias B0. We show the results in the figures as follows. Black lines refer to the standard dataset, while red lines to the extended. Thin dashed blue lines show the reference values. The concentric lines describe the probability contours of 68% internal line and 95% external line confidence level. From our study, we obtain that the use of the extended dataset can, in some cases, improve the constraints on cosmological parameters. Depending on the set of varying parameters and on their prior knowledge, the improvement can be mild, in particular for parameters that are mostly degenerate with neutrinos mass and affect the matter power spectrum at all scales. This is more evident in this other triangle plot, where we consider, instead of the bias B0, the amplitude AS of the matter power spectrum. Varying AS results in rescaling the matter power spectrum at all scales, as we can see in the figure in the upper right, and it is strongly degenerate with the sum over m nu, as highlighted in the green box in the triangle plot. To conclude, we have realized a complete pipeline to study the impact of the addition of information about large-scale modes of the matter-power spectrum on cosmological constraints. In particular, we have shown that it's worth exploring the potential of the large-scale reconstruction method to study cosmologies beyond the standard lambda CDM. We have also obtained some original products. A mathematical code for the reconstruction of the matter-power spectrum at large scale, a Python code for the MCMC analysis using the Cobaya software and run on a HPC cluster provided by Cineca, a Python code in Jupyter Notebook for the statistical analysis of the MCMC results using the GetThis software, a Python code in Jupyter Notebook for the study of the impact of the cosmological parameters on the matter-power spectrum. Despite being very simple, the present work sets the basis for immediate extension. For example, addition of redshift space, distortions, effects, and more complex expression for the bias, study of extended cosmological models, calculation of more realistic data covariance and more refined likelihood function, application to n-body simulation for testing the reconstruction on more realistic synthetic datasets. Thanks for your attention.